Thank you very much. And then now we have a chance to ask questions on this EUV issues. And then we're going to have panel discussions. First, maybe you have questions to their talks. Okay. No questions.
Thank you very much. That was really interesting. I actually have several questions. I'll start with one. Let's see. Okay, so I'm trying to understand the situation regarding active regions. Okay, so you know, you guys didn't talk about it too much, although you touched on it a little. But active regions are why solar max is more EUV than solar min. At solar min, there are no active regions, but then Frank showed us there is variability. So what are your thoughts on active regions? Has anyone tried to develop an active region-based model where they say, hey, I'm counting the active regions, each active region has this much EUV, and here's its geometric projection or something like this? So anyway, I just want to get your thoughts on that, because I think it's interesting.
So that's exactly one of the ways in which you can model EUV, which is to define different types of solar pixels. Take one of those images and say, look, we've got a quiet sun, we've got faculae, we've got active regions, we've got flares. Each one has its unique spectral component, and then you simply add up how many pixels of each type and then add that spectrum together, the spectra together, and get a... So it is a way in which people try and come up with a model of the solar EUV irradiance and actually the entire solar spectrum based on solar images.
I'll comment on that too. People like Juan Fontenla have made models just like you're talking about, using images of the sun at different wavelengths and breaking it apart into maps of different temperature regions essentially, and then assigning a spectrum to those. And Juan's model has worked very well in the visible and infrared. It's much more complicated in the EUV because there's a lot of three-dimensional structure, and a flat 2D picture of the sun is not capturing all of that three-dimensional structure of active regions and loops and things. So while we're progressing towards that, the models aren't really that good yet. But I think all of us recognize in the EUV modeling community that we recognize that the future is probably going to be image and irradiance combined. More questions?
A number of years ago, a calcium plage index was used for some things, and I was just wondering how that fits into the picture these days. And that was one based on active regions.
Right, and that's used very well for chromospheric variability, but it doesn't capture the coronal and transition region variability, which is dominating the EUV. So it works well for the far ultraviolet and middle ultraviolet emissions on the sun, but not so much the shorter wavelengths.
I was just curious, struck by the high frequency variability that you illustrated toward the end of your talk. Would that be activity associated with the solar atmosphere, the coronosphere, where there's known to be quite a bit of wave activity?
They're all for me. Yes, actually. All of the really high time cadence changes are happening in the corona and are driven by magnetic changes in the corona. The corona is highly ionized, and magnetic fields are changing very rapidly and moving and heating and cooling the small pockets of the sun and of the plasma. And during flares, you get spots on the sun, just a few loops, that are brighter than the whole rest of the sun in the EUV and X-rays. And so if you're not looking at the high time cadence, you're not going to see all of that.
Now, two questions. One, people who model the ionosphere, and maybe this is for Phil, typically find that the E-region electron density that comes out of the models is too low and compared with observations. And one idea is that it's basically the X-rays that are being used in the models are too small, that they're missing lines in the X-ray region. I know Stan Solomon has been proposing this. One way to fudge the models is to increase the X-rays by something like a factor of 4, which sounds like it's pushing things pretty far. So just one thing as a general comment on that, and just a more specific comment for Frank, is what is being done to ensure the long-term stability of the GOES measurements.
Yeah, on I would say doing too much to the X-rays, soft X-rays, is a problem, because all the comparisons I've done with the photoelectron flux, which is another monitor essentially of that region, it wouldn't allow a big increase in that region. And you're right. September 2005, I showed for Millstone Hill, the agreement between the model and data in the E region was pretty good. But most of the time that's not true. And we still have a problem which amounts to something like a factor of 2 in the production rate. So it's a big factor. And we're kind of stumped at the moment on what is the reason for that.
So from the solar measurement side, I can say that through much of the soft X-ray region, we've reduced the uncertainties of the measurements down to maybe 30 to 50%, not factors of 4. So if the models aren't doing the right thing, we're limiting how much you can actually crank reality to make it work. As for your other question with GOES, we have built in several different levels of degradation tracking. Most of it is based on the fact that we're measuring the magnesium 2-core to wing ratio, and that's a calibration independent measurement because it's a ratio. So if the instruments are degrading, the magnesium 2-core to wing won't degrade, and we've developed what we call a bootstrap method to transfer that degradation or lack of degradation to the other 2 channels and be able to correct it in real time. And we've tested that out using time C data.
Thank you so much. Thank you very much. I was wondering if which of the measurements, you were mentioning the EVE measurements, if they have high enough resolution to resolve line shape changes over the solar cycle, and then also, is there a central place to access all these data or to access the websites to then access the data, please? Yeah, thank you.
So the answer to the first question is that no, we don't resolve the solar lines themselves. You would need milliangstrom resolution to do that. Our main customers are atmospheric people who care less about that than the solar people. And the data is all available if you go to lasp.colorado.edu and either /EVE or /C, and all of the data for both missions is there. We also have a limited subset at our LISIRD website, LISIRD, which is the LASP Interactive Solar Irradiance Data Center. And that's also just lasp.colorado.edu.
I have a question about real time and using that 81-day average 10.7 centimeter flux or magnesium decor or whatever that you need to do in the modeling. I know that Oleg Troshyshev has done some real-time stuff where he needs to estimate things like the IMF-BY on a long-term basis, and he's able to do it more or less for real-time work. Can you implement those kinds of extrapolation and interpolation estimates to be able to do the same for your 81-day average?
Yeah, you can. Of course, one of the problems will be when you're on a very steep decline over many, many days. It's hard. You can extrapolate, you can guess, you can forecast what will go out. Even IRI today uses a 12-month running average, and people try and use the forecast of the solar cycle in sunspots. So you can either use a forecast, or you can just use the previous some number of weeks or months to try and come up with a way to average and weight the average so that you get rid of the overestimation of the solar modulation. Again, all of them will have pros and cons and strengths and weaknesses. Probably none of them will do as well as doing a full 81-day centered average on the date. But people have been fairly successful. Kent Tabisca, for instance, in his Solar 2000, has really done quite a bit of work on trying to figure out the best way to come up with a real-time solar irradiance proxy.
And another way to deal with that is, as opposed to using just an 81-day mean and the real-time number, is to break up the variability into different timescales. So Phil Chamberlain's FISM model, which is based on CData, he has a solar cycle spectral variability that's driven by one set of proxies, a solar rotational variability that's driven by another set of proxies, and a solar flare variability that's driven by another set of proxies. And so you can reduce the error by breaking it apart into different timescales.
Is it possible to take a real-time solar flare measurement and incorporate that into your 81-day running average and get something a little better?
If you've got measurements of the EUV and the X-ray, you don't need any 81-day averaging. So the ultimate answer is to not use a daily proxy or any of these other proxies, because they're not really measuring the EUV. If you measure the EUV flux, presumably you wouldn't need any averaging at all, and I think that's what we all advocate for any kind of real-time operation.
I was intrigued by the comment that Art made about the E region, and that Phil agreed with him, that the modeling of the E region isn't as firm as we might have thought. In other words, if solar terrestrial physics has ground truth, shouldn't photochemistry in the E region be the cornerstone? And then we say, well, in the F region, we understand photochemistry. All the complications come from dynamics of electric fields and winds. So is the modeling of the E region really as a factor of 2 or 4 as you suggested? And that, what's wrong? Do we not understand photochemistry? If you're using the right fluxes in the right neutral atmosphere and EMSIS agrees with it, why hasn't the E region been successfully modeled?
This is probably a question that's better directed at Stan Solomon, but he's not here, so it is a mystery. We think we know the reaction rates pretty well, and there does not seem to be a lot of leeway for changing the solar flux in the required region. So it's a mystery. It's really frustrating that we can't do better.
Was I misled in my recollection that John Titteridge's model of the E regions worked fairly well, and that is it the global circulation maybe models that that are having difficulties?
Well, I mean, in the E region, there's nothing to do with circulation. It's just straight chemistry and photoionization, basically. I don't. And Stan's done a lot of work on this, and we basically come to an agreement that the difference is typically something like 30 or 40% in density, which doesn't seem a lot, but when you realize the reaction rates are electron density squared, then, you know, if it translates into a production rate, then you're talking a factor of 2. So that's what, but I don't know what you can do about it.
For the E region, how are the models doing with the metallic ions that are present there? That seems to be a very variable factor that might be really difficult to account for.
We typically don't deal with the metallic ions.
Well, there's a possible explanation for much longer lifetimes of the ions that would reduce the need for higher production rates.
Well, I would expect they'd be sporadic, if I remember correctly. And this is a kind of a general problem.
One question from me. This is probably simple and has an obvious answer, but why do you pick 81 days instead of 83 or 79 or something like that?
Ask Hinderrigger.
Yeah, it's 3 solar rotations. That's historically why. Phil Chamberlain actually did a study on that for his dissertation of what time scale gave the best average to use in a proxy model, and he ended up that after 54 days it didn't make much difference. So his model uses a 54-day average.
Okay. Has anybody actually looked into any other kind of averages other than those? I guess those are the best.
When I did some work with the calcium plage index way back in my early part of my career, we found that those regions would sort of grow and dissipate. Sometimes you'd only see it once across a solar rotation, sometimes a couple of times. So the 81-day average really doesn't take into account the growth and disappearance of those active regions, and perhaps some other modeling within that rotation period or the 81 days could account for some growth and decay of the active regions.
So actually, the point of the 81-day average is not to capture that rotational variability or active regions coming and going. It's to capture the background of like solar cycle type changes as opposed to the shorter time scales.
So I have a question and sort of a comment / question. So the first question is, can you tell us the difference between like the E10.7 and the magnesium?
Yeah, so Kent Tabisca is the one who's, at least I'm familiar with the E10.7, and his goal was to provide ionosphere-thermosphere modelers with a number that they could just plug into their model and not have to change anything. And I think that's a good philosophy. I think it's up to us solar physics and solar monitor people to come up with what's needed by the community rather than give you a spectrum of 6,000 lines and say, here, it's everything you ever wanted and more. So let us try and work that. And that was his attempt, is to come up with a value that mimicked F10 so that the models wouldn't have to change. But he incorporated 304, he incorporated magnesium. He pretty much captured anything he could find. And they're working very closely with the neutral density as measured by the satellite drag down to the Air Force tracking satellite drag. And so they've got an empirical model. And each one of these new proxies or measurements gets added to the model that removes one layer of variability, and it's left with something that was hidden before, and then they find something else to correlate with that. So they've got a very good empirical set of inputs that helps them drive their model. E10.7 is just one of the ways in which they tried to put all of that into a single number. Now, as we say, it's not going to capture everything. And I like to point out that since F10 is already a proxy, now we have a proxy for a proxy. And this starts to get a little bit far from reality. Why don't we just go back to the real measurements and try and figure out how to use the 304 or some of the actual EUV emissions in the models? And again, that's where we come on. Phil's been working on his EUVAC model to try and make that jump so you don't have to try and just keep using F10.7. Or, that's the classic when asked, what is it that the ionosphere-thermosphere people want? They want better F10.7. And I don't know that we can do that.
All right, so then the second comment question is that in flares, it's not really the size of the flare or the peak value of the flare that matters, it's the integrated energy. So is there some sort of, there's like an M class or an X class flare, is there some sort of class that actually captures the integrated energy, and if not, why?
Well, so in our forecast center, we capture flare initiation time, flare peak magnitude, and then the half height return, and that gives you a flare duration. So all of that is captured in a database, but that's only for the X-rays. So we're only looking, because that's what is a primary driver for a lot of the other space weather. As Frank points out, that in the extreme ultraviolet, every flare is completely different. So now you would need that sort of integrated flux or fluence for every wavelength, or every critical wavelength. And so, I mean, again, we can provide that information, but it starts to become, you know, every wavelength and then every time step, and we would have to be selective as to which are the most critical in terms of the drivers but I think you could easily do that for some of the primary emission lines and the major energy sources.
With EVE, we've measured several thousand flares now of all different sizes. Only a few X because we've got a very disappointing solar cycle. But as Rodney said, we're capable of creating indices. We just haven't figured out what the best indices are. And I think that is going to have to be based on you guys and different interests. An ionospheric index for a flare might be different from a thermospheric index for a flare because different wavelengths matter for heating as opposed to ionization and things like that.
Yeah, so I mean, when we're trying to like compare different flares, we look through a database and say, this is an X5 flare and this is an X5 flare, and then we run those through the thermosphere model, and we obviously get very different results. And most of the time, it's because the duration of the flare is very, very different.
It's a great discussion and a great dialogue, and unfortunately, it's time to end this panel discussion. If you have some final words to this community, do you want to say something?
No, we would like to hear from you on which of the many approaches that are possible in terms of providing the best data-based, observation-based information for driving models. I mean, we can come up with a Hinterrigger 30 and Richard's 37 wavelengths, or there are many parameterizations, probably provide more information than you need, but how can we reduce it down to the critical information so that the models aren't overly burdened by trying to run with too much information? I mean, it's a part of a dialogue, as Frank said.
I'll just reiterate what Rodney said, that the measurements of EUV irradiance are for you guys. And you need to tell us what you really need. We can guess, we can put out data products, but we have this fire hose of data from EVE just spewing down every 10 seconds, full spectra. What do you want us to do with it, to give it to you?
Well, I think, as somebody said, that depending on what you want to do, is what data you need. For a lot of modeling, a model based on C data would be all we need. For the things like Aaron's talking about, for flares, you need absolutely the best information you can get and the highest time resolution. So it really depends on the application. If you're modeling 1 hour ionoson data, you don't want 5 minute, probably you don't need 5 minute solar EUV, so, or 10-second.
Okay, thank you very much for sharing your insights, and then